modeling and related things. So now he is here. So for next 2 hours he is here with you. After that we will have the class at 6 p.m. Today's 12 to 1 class because of some prior commitment we are not having. So we'll be meeting at 6 p.m. after this session. Yes. So he has been teaching various courses like basic electronics, VLSI engineering, introduction to electronics device labs, and introduction to electronics labs, technology and process modeling, etc., etc. He has bagged many of the awards like Early Career Research Award from DST Government of India, Best Paper and Best Manuscript Award from ICEE in 2018, Golden River Award from Electron Devices Letters and Transactions on Electron Devices, the Student Innovation Project Award at doctoral level, and likewise he is having many things to his credit, like he is reviewer of many of the very renowned journals which are there in the electronic and circuits. So over to you, sir. Dr. Gaurav, can you hear me?
Yes, Dr. Jadhav. Thank you very much for the, thank you for the kind introduction. So, so I hope that all of you can hear me very clearly, right? And
yes,
I also hope
sir, we
that
can hear you very clearly. And
is my screen also visible? The part
yes,
that I am sharing?
Yes, it is. Yes, okay. Whiteboard is there, quite visible. Yes, sir, please.
Whiteboard is clear. Okay, great. So, can you please also check, is my cursor visible? I am moving my cursor. Is it visible? Dr. Jadhav, can you please just confirm? Cursor. I am just moving my cursor. That is not visible.
It's visible. It's visible.
Is visible, right?
It's visible. Yes, sir. It's visible.
Okay. Thank you. And if I am writing something here, is that also visible?
Have you written something? Just try to.
In the top.
Yes, sir. It's visible. But make it full screen so that it's going to occupy the full screen. If you can.
Is it not? I think you can do it from your end. I'm just sharing one of the window.
Okay. Fine. Thanks. Okay. Thank you so much, sir. Please proceed.
Thank you.
Please.
So good morning, all of you. Myself, Gaurav Datta. So I hope all of you are doing very well, right? So today we are going to discuss a topic which is on the signal generators, okay, consisting also of oscillators and different waveform shaping circuits, right? Please feel free to stop me whenever you feel you have any doubt or you have any question, okay? So what is signal generator? Right? All of you know that what is signal generator. Signal generator is an electronic system by which you can produce different electrical signals. Right? Different electrical signals means it can be having of different waveforms. Right? So, and you should be able to vary its frequencies, its amplitude, right? At the same time. And where you can use the signal generators, you can obviously use the signal generator as a source of signal and also use it for different testing, designing of different circuits as well as troubleshooting different circuits. Now, to start with the signal generators, couple of points. So, you should remember some of the points are like these electrical waveforms. What do you mean by electrical waveforms? Typically, if you say like electrical waveform means either sinusoidal wave or square or rectangular wave, triangular wave, all different type of pulses if you are using this data. Right. As I already mentioned, these are used for simulate for different testing, different type of circuits.
No problem.
Okay. And here common types of these these different types of signal generators can be just.
Please take care that for next 2 hours. I'm so sorry.
Okay, so common types of the signal generators are these function generators. I think all of you have used these function generators. And there are also other types of the signal generator. For example, RF signal generator that can generate signals at a very high frequency. Then arbitrary waveform generator. Okay, and that means it is not a regular shape. Depending on the input of the user, it can generate these waveforms and different type of pulse generator as well. Among this, we'll try to cover different types of function generators and some part of this pulse generators as well. Right. And as I already mentioned, the output frequency, amplitude and waveform, these are usually adjustable. You can vary. For example, a same signal generator, for example, this is a typical signal generator. Here there is a knob which is called waveform. By pressing this knob, you can choose between different waveforms. You can choose between sinusoidal, triangular and square waveforms. And there are other knobs as well. For example, different parameters. By clicking on the parameter, you have options for adjusting the amplitude and then frequency. There is a knob, you can rotate this knob and adjust those amplitudes, as well as this modern signal generators do also provide this type of numeric keypad. So here you can enter the magnitude and enter the value. And there are, say, third one is the unit. So here this unit means you can change, suppose you want to give it some in millivolt. Okay, then no need to change this knob so much that go to the millivolt. You can directly press this unit and change between volt, millivolt, like that. And if you are suppose sourcing some type of current, then that also you can adjust from these different units. Right. There are other things like for example sweep, okay, then trigger, then below you have some shortcut keys, for example different waveform generators, which type of waveform you want to choose, you can directly select those from. You can see here there are two channels have been provided. So this is channel 1, this is channel 2, and these are the BNC connector. So you can use the BNC connector and take the generated waveform from here and use it for your purpose. And if you check carefully in a practical signal generator, you will see here one resistance would be written here, that is written as 50 ohm. Okay, this 50 ohm, this is very important, this is the match load, right? So this should be there, okay, 50 ohm. Here this is for different purpose, this is for syncing this signal generator, that probably we will not discuss here today. Here there is, you can see there is an USB port. This USB port typically for this instrument can be used for transferring data or maybe loading data. For example, I have also mentioned that it can be used for arbitrary waveform generator. So arbitrary waveform generator means the signal can be the user defined signal. So that user defined signal you can use using pen drive, load the MATLAB code in your pen drive and just plug it, and this function, this generator, waveform generator will take the code from here and produce the actual signal. Now modern signal generator also can perform different type of tasks. For example, you can just simply add these two signals, okay, addition, subtraction, those type of things are also possible using this type of signal generators. Now here you can see these basic signal generators are typically consist of the following key components. What are the most important components? The most important components are the oscillator. Oscillator is the most critical part. Then it is the frequency control. You should have the amplitude control. Then waveform shaping circuits, if you want to change it between different waveforms, and then output stage for the matching and this transferring this power so that the maximum power can be transferred and to match the load between the signal generator and its output. So that basically deals with this output stage. So what is oscillator? Oscillator, this is the core part of the signal generator responsible for generating this periodic signal. it produces a continuous waveform of a particular frequency, right? So it always produces the waveform of a particular waveform, maybe it's a sinusoidal wave, triangular wave, or and square wave, but the frequency will be always constant if you are not changing the circuit. Then you should also have an option in this oscillator for changing the frequency. So this allows the adjustable frequency for the signal to be being generated. It can be typically been done by using variable resistors, capacitors, digital control systems, or maybe using different PLL, phase lock loop circuits. Then amplitude control. This part of the signal generator will allow you to change the amplitude or the voltage level of the signal. It can be a simple variable resistor, or it can be a more complex automatic gain control circuit by which it will allow you to control the amplitude. Then the fourth one is waveform shaping circuits. To create different type of waveforms such as between sine, square, triangular, then sawtooth, and various other waveform shaping circuits can be employed. This includes different type of filters, mixtures, and waveform generator designed to shape this output as desired. Then the last one is the output stage. This is the component that delivers the generated signal to the external load. Okay, to the external load means it may be an oscilloscope or maybe a test circuit or test equipment. Okay. This might involve these buffers. You already know what buffer is. Amplifiers, impedance matching circuits to ensure that the correct voltage and the correct levels has been provided. These are the basic components or the parts of a signal generator. Now, as we have already discussed that the primary component is this oscillator. So let us focus and spend more time on this oscillator. So what is the basic principle for this oscillation, or how does an oscillator look like? So oscillator actually it consists of an amplifier and a feedback network. You can see this is an amplifier whose gain is noted as A, and this is the feedback network whose transfer function has been denoted as this B. Transfer function means this output voltage by input voltage. Okay, means for this case it is VF by V out. Okay, and here this is the mixture. So here this is the input signal. So we have considered input signal as V in, and here I have drawn plus, so that means they are in same phase. So these two signals basically add up and give the resultant here signal here. Okay, so this is a typical oscillator circuit. We'll go into more detail. Now here, if you see this circuit which is drawn beside it, so this circuit, actually what is the difference here? You see, it is plus and minus. So that means what? That means this signal and this signal, they are out of phase. Okay. So here, as a result, you can see this is V in, and if this signal is VF, and what is VF? As I already mentioned, if this is V out, then V out into beta, that would give you this VF, right? So that is VF. So then what would be this signal? This signal would be given by this V in minus beta of V out. Right? Now it will fit into this amplifier whose gain is A, and it will produce this output again. Right? So this is an example of a positive feedback system. This is an example of a negative feedback system. Right? So in this positive feedback system, if you consider, as I already mentioned, this is V in, right, and this is VF. VF is equal to beta V out. And what will be the resultant signal here? After this mixture, resultant signal is given by this V in plus beta V out. Right? So then what is V out? Here, V out is whatever be the input signal here, that would be multiplied by A, gain, right? That would produce this output voltage. So that I have written here. So you can see this V output voltage is equal to A, this gain, into the input. Input here is V in plus beta V out. V in plus beta V out. Now you can see here also you have V out, here also you have V out. If you take all the V outs one side and V in on the other side, and then take the ratio of this V out by V in, you will get this thing. So it is V out by V in is A by 1 minus A beta. Right? This is for the positive feedback system. Now if you consider this system where we are using this negative feedback, this V out by V in, it turns out to be this A by 1 plus A beta. So only difference is this sign. Here it is minus and here it is plus. Right. Now, if you connect any amplifier and any feedback system in this configuration, that will not ensure that you will get the oscillation out of it. To get that oscillation, you have to satisfy some criteria, and that criteria is called this Barkhausen criteria. This Barkhausen criteria says that the magnitude of the loop gain has to be equal to unity. Now what do you mean by this loop gain? Loop gain means gain of this entire loop. Now what do you mean by loop? Loop means this loop. This loop. So here what is the gain? Gain is A. Here what is the gain or attenuation? Basically this is a passive network. This network is actually passive network. So it will not provide any gain amplification, but it will attenuate the signal. So that's what I am saying, attenuation. So A into beta, that term would be equal to 1. So you can see A into beta, that term would be equal to 1. Now you can also see that I have used this mod. Why I have used mod? Because if it is the positive feedback, right, then it would be A beta would be positive. But if it is a negative feedback, then A beta would be negative. Because here this amplifier would produce a gain of A, and at the same time it will also create a 180-degree phase shift between this input and output. Right? So because of that, one minus sign would be there. So to generalize it, we have written it like this: AB mod, this is equal to 1. The second criteria is that the phase shift around this loop has to be 0 or any integer multiple of 2 pi or 360 degree. Right? So that means the total loop phase shift has to be equal to 0 or in multiply of 360 degree. What does that mean? For example, if you consider this part, of this, then this is a positive feedback case. So here this amplifier would not create any phase deviation at this output. Whatever be the input, the output signal would be in the same phase. Similarly, this is the frequency selective network or the feedback network. This feedback network will also not produce any shift in phase. So as a result, what is the total shift in this loop? It is 0 and 0. So total shift would be 0. However, if we consider this part, that is the negative feedback part, here this amplifier will produce a negative phase shift, means 180-degree phase shift. Right? This 180-degree phase shift will be produced by this amplifier. For example, if you are using a CE amplifier, then CE amplifier produce 180-degree phase shift. Then you have to be careful in choosing this beta or this feedback network such that this feedback network should also produce 180-degree phase shift. So then what will be the total phase shift? 180 plus 180, 360 degree. Right? So in that case, you can expect you will get a sustained oscillation out of it. So I hope then this part is clear to you, that two criteria it has to fulfill. The first criteria is on the in terms of gain, where this loop gain A beta has to be equal to 1, and the second one is in terms of phase, where it says that the total phase shift around the loop has to be 0 or integral multiple of 2 pi. Now here a couple of things has to be noted. Any circuit may employ either positive or negative feedback depending on its intended function. Right? Now the positive feedback is typically used in designing these oscillators. where the goal is the sustained periodic signals without any external input. However, for negative feedback, it is commonly used to stabilize the system, to improve linearity and this to reduce distortion. So, and both types of feedback, however, both types of feedback can be used to design these oscillators. Okay. So both positive feedback and negative feedback can be used for designing oscillators. However, most preferably and typically, the positive feedback has been used for designing these oscillators. Now, for example, if you see this diagram, right? So it shows a typical block diagram, right, of an oscillator. So maybe to make it more generic, let us consider that this is having a negative feedback. Okay. So it has a negative feedback. So if it is a negative feedback, then what will happen? You know, this should be producing 180-degree phase shift and this part should be able to produce 180-degree phase shift, right? And this A and B, these two multiplication would give equal to 1, mod of A beta would be equal to 1. But if you compare it with the earlier image, here I have written S, A is and this beta S. Now what this S signifies? You know, this S is basically j omega. So it shows or indicates that this amplifier response is also frequency dependent. That is the case, you know that, right? This feedback network, which is a passive network, this passive network response is also depends on the frequency. So to denote that, we have written AS and this beta S. Okay. Okay. Now, how can you design these oscillator in terms of circuit? For example, we need an amplifier, this amplifier, which can produce 180-degree phase shift. So we can use different types of amplifier. One of the amplifier using op-amp, we termed it as inverting amplifier. So this is an inverting amplifier. Why we are using inverting amplifier? No, not the not inverting one, because here we are assuming that this is producing 180-degree phase shift. And you know, if you are using an inverting amplifier, that will also produce 180-degree phase shift. So this is that inverting circuit. Okay, non-inverting amplifier. So here you know how to design this. This part is grounded, and here this is resistance R, this is resistance R2. Then what is the gain? Gain would be equal to R2 by R, feedback resistance by this resistance with a negative sign, right? Okay. Now how can we design this component? That is beta, or this frequency selective part. The frequency selective part can be designed by using a combination of R and C. For example, in this particular case, we have designed it RC connected in this fashion. Okay. R and C connected in this fashion. Now it has to be connected properly. So how do you connect it? Here, let us take the output. Let us use this color only. Let us take this output. This output has to be fed, right, to this beta. So this entire part is now this beta of S. Okay. And this is acting as this A amplifier. Okay. So you have connected this output to the input of this beta. So beta is this entire block, right? And what about this other terminal? Other terminal has to be connected back to the input of this amplifier, right? So we are feeding it back to the input of this amplifier. Now this will construct an oscillator, and this oscillator is called the phase shift oscillator, that we are going to discuss in the next page. Here it is important to note that 180-degree phase shift that I have already mentioned, that 180-degree phase shift would be provided by this part of the network. Remaining 180-degree phase shift would be provided by this 80-degree network. When I am saying that this would produce 180 degree and this would produce 180 degree, yeah, this will always produce 180 degree phase shift, but this part does not, right? You have to be careful in designing on choosing the values of this R and C such that this total combination can produce 180 degree phase shift. Okay, so if we can do that, then what is the total phase shift? Total phase shift is 360 degree. That is okay, 0 or 360 degree, right? So Bart Hussein, one of the criteria is satisfied. Then to satisfy the other criteria, we have to ensure that the gain produced by this, okay, if this gain is A and the gain or the attenuation produced by this, that is beta, right, this has to be equal to 1. If we can do that, then as a result, what we can expect, this circuit would produce an sinusoidal waveform. Okay. It does not require any input signal. It does not require any input signal. But simply by connecting the circuit in this fashion, it will produce the sinusoidal signal. Let us see this circuit in more detail in the next page. So this is the phase shift oscillator. This is the same circuit actually what I have drawn in the last page. Okay, but there we have used only one op amp, but here you can see we have used 3 op amps. But do not worry about it because these op amps are used. See how these op amps are used? These op amps are basically used as a buffer, right? See, it's this inverting terminal has been connected with the output. So that means this gain of this part is actually 1. And why do we use it? I will discuss this after some. And I hope that you have recognized this part of the circuit. What is this part? This is that inverting amplifier part. So this is that inverting amplifier part having feedback resistance R2 and this resistance R1, series resistance R1, right? And so this is the amplifier A part. And this part is this beta part or this feedback frequency selective part. Remember why we are saying this as frequency selective, because depending on the values of R and C, it will allow or it will means able to pass only one selective frequency only. Okay, so that's why it is called a frequency selective part. Now, if we have to analyze and really find what are the frequencies and what would be the really the criteria of choosing these values of R, C, this R2 such that we can get this oscillation. So we have to derive these things a bit check what are the relations between this output voltage and this input voltage and intermediate voltages. Then we should be able to tell the relations between this R, C and this R2. So let us do that. For example, if we consider the first part of the circuit, that is this part of the circuit. So here it is V in and here it is V1, right? Here it is V1, but it is what? It is simply a buffer. So whatever V1 is here, the same V1 you will get here. So for the time being, you can ignore this buffer. So just consider this part, this C connected with this R, this C connected with this R. Then what would be this V1 in terms of V in? So we can simply write it like this. V1 would be equal to what? Whatever drop across this R, so it is R by 1 plus AC. Now what is S? S is j omega. You know what is the impedance of an capacitor? 1 by j omega C, right? So then S is j omega. So you can also write it as 1 by SC. So that's what I have written. R by C means 1 by SC plus R, right? Series combination into V in. So this can be easily written like this. So this is the relation between V in and V1. Now similarly, if we have to find the relation between V2, that is this, and this V in, how can you do that? Okay, it is not difficult. because you know what is the input V1, right? For this case, this C and R. So it is R again, R by R plus 1 by SC into V1, because V1 is the input and it's the same value of R and C we have used everywhere. So it is the same thing, same transfer function. So that would give you this again the same thing what we have calculated here, right? Into this V1. Now what is this V1? V1 in terms of V in we have already derived. If you substitute this part, then it comes out to be this V out is SRC by 1 plus SRC square into V in, right? But we need to find this part, right? What is V3 in terms of this V in? Right? Is it a different circuit compared to this part? If you consider, it is not. It is the same thing, right? Why? Because you see this is the capacitor and this is the resistor, right? Whose value is also resistance is also R. And if you consider this op-amp, this non-inverting terminal is grounded. It's a physical ground, and you know op-amp property. So if this terminal is ground, then that will also make sure that this terminal is also virtually grounded. So here the potential is also then zero. This potential is also zero. So that makes, you see, this V2 connected with this capacitor, this connected with the capacitor, then it is this R, and then R is being virtually grounded. So it is the same thing as the previous two, right? C and R. Then we can also then, if you just proceed use the same logic, then what you can write? V3 can be easily written as SRC by 1 plus SRC cube into V, right? Okay. Now, what is this actually? If we know this V in and if we know what is this V3, and if we find what is V3 by V in, actually what is this V3 by V in? V3 by V in is nothing but the transfer function of the frequency selective network. So what is the frequency selective network? Frequency selective network is this part, right? And we have denoted it using beta, right? Beta is. So this is nothing but this frequency selective network transfer function. So it would be given as this SRC by 1 plus SRC cube, right? So we are able to find what is the expression of beta. Then to calculate what is the loop gain, we should also know what is the gain of the non-inverting amplifier. So non-inverting amplifier gain, sorry, this is an inverting amplifier. I have written here non-inverting, but it is not the non-inverting, it is the inverting amplifier. So it is the inverting amplifier. What is the gain? Gain is simply by R2 by R, right? With a minus sign, but I am using this mod, R2 by R. Then what would be the loop gain? Loop gain is A into B or A into beta. So if you multiply this and this beta, that would give you this as the entire loop gain, right? And as per Barkhausen criteria, we know the condition for oscillation is mod of AS into beta S, that would give equal to 1, right? So that means this is equal to 1, right? Now if this is equal to 1, right, then what can we write? This S, I already mentioned S is basically j omega. So just replace this S, j omega. These are cube. Try to simplify it. Remember this j is root over of minus 1. So j square means minus 1, right? So take care of those parts. J square put minus 1. Then you will get a simplified version of this mod of S and beta S as this R2 by R1 minus 1 j omega RC, this cube, by this part, right? Okay. Now here is the catch. Now this is the expression, right? And here in this expression you can see it is a complex number, right? This is a complex number. But as per Barkhausen criteria, it says that it has to be equal to this term. this has to be equal to 1. So that means this has to be real term. So how can you make this term real? So you can see here, this numerator also you have j, denominator also you have j. So it is not possible that omega rc should be equal to 0, not possible, right? So the other way you can think of it is that if we can make this part equal to 0, right, then here is one j, here is one j, this j, both of j would cancel out. That would make this mod of a into beta a real number. Okay. So that means if we say this is equal to 0, this part is equal to 0, then this number would be real. Now considering that criteria, we can write this. Now from here we can find what is the value of omega. So omega is then from here 1 by root 3 into 1 by RC. Now this omega is not any angular frequency, but it is the angular frequency during oscillation. So we have used the term omega naught. Okay. So we have used the term omega naught to denote that this is the oscillation frequency. I hope this part is clear to you. Then add omega equal to omega naught. Okay. If anyone wants to calculate what would be the magnitude of this mod of AS and beta S would be, right? Then just simply substitute it. Okay. Just simply substitute it, right? This gives out this expression that mod of AS into beta S turns out to be R2 by R1 into 1 by 8. Okay. Now we already know from this Barkhausen criteria that this part has to be equal to 1. So that means this term has to be equal to 1. So you have to choose the value of R2 and R. I think I have to be careful here. Please note one thing. I was using here R. Okay. So this gain is here R2 by R. This part up to this is fine. But I think here I have written R2 by R1. So that will not be R2 by R1, but it will be simply R2 by R. Okay. R2 by R. Is R2 by R. So that means what? That means that this part has to be equal to 1. So how can you make this part equal to 1? If we choose this R2 by R value equal to 8, then 8 into 1 by 8, that would make it equal to 1, right? And remember the negative sign we have already taken care earlier, right? So that gives us the criteria how we should design this amplifier part. Okay. Now here are a couple of interesting things one should note. For example, if you consider only this part, okay, let me choose this color, a light color. Okay, let me consider only this part, this RC network part. Okay, so you can see there are same 3 RC networks has been used, right? I already discussed, right, why this is also similar. These 3 are similar to each other, right? Because of this virtual ground, right? Okay. Now we are considering one of the situation here. So what is the situation? The situation is that here is V in, this is the V1, this is the first case, C and R. Now we have also written this transfer function V1 by V in, and we have seen that it comes out to be like this, right? Just try to simplify it. Okay, try to simplify it and consider that here omega is the omega naught. So we know what is this omega naught RC. Omega naught RC, we know omega naught RC from here, right? Omega naught RC equal to 1 by root 3, right? Then substitute this omega naught RC is equal to 1 by root 3. So when you substitute it, right, you get an expression something like this. Okay, again you can see this is in both real and imaginary parts are there. That is expected because it is a simple RC network. So in this simple RC network, you have already this expression, right? Now from this expression, this transfer function, if you try to extract what is the phase and what is the magnitude, that also we can easily do. How do you find this amplitude? Amplitude is root over of the coefficient of real part plus root that square plus means root over of a square b square, right? So that you can easily find. So it become 1 and root over of this root 3 this part. And what is the angle part? This is only j, so that gives 90 degree, and this is tan inverse 1 by root 3, so that means 90 top, and the below it would be 30, so it is basically 90 minus 30, so that gives 60 degree. 60 degree, and if you calculate this part, this turns out to be 1 by 2. So the magnitude is half, and the angle of the phase, that is 60 degree. So that means between this and this, right, the amplitude would be reduced by half, and there would be a phase difference of 60 degree, right? Now we recall that there are three similar networks are there, right? Same networks are there. So, and we have just now seen that this is producing a phase shift of 60 degree. Next part is producing a phase shift of 60 degree. Third part is producing a phase shift of 60 degree. Then what is the total phase shift? Total phase shift is 180 degree. Right? Total phase shift is 180 degree. And the other 180 degree phase shift is given by other 180 degree phase shift is produced by this inverting amplifier. Right? So this is 180 degree, and each block is producing 60 degree, 60 degree and 60 degree phase shift. Okay. Then the total phase shift in the loop is becoming 360 degree. So that means this output and this input, they are in the same phase. Okay. So then one of the criteria is satisfied. Okay. Next, you also please check it out. What is this amplitude? Amplitude is half, right? So as I already mentioned, this amplitude is becoming half. So that means if it is V in, so here you are getting half of V in, right? Now this half of V in acting as an input to the second stage. Then what will be the output? Again half of V in. So that means V in by 4. So you are getting here V in by 4, right? So this V in by 4 acting as an input to the third stage. So what you will get at the output? It would be V in by 8, right? Then whatever the input you are giving here and whatever the output you are getting for the feedback loop. So if you are giving here V in, so after this feedback loop, it is becoming V in by 8. So then what is the attenuation? It is 1 by 8, right? So attenuation is 1 by 8. And what is the relation between R2 and R? R2 and R is relation is, we have already derived, it is 8. So 8 is what? 8 is nothing but the gain of the inverting amplifier. So inverting amplifier gain is 8, and this beta network or this frequency selective network, this attenuation is 1 by 8, right? Then what is the overall loop gain? Overall loop gain turns out to be equal to 1. So that satisfies the other criteria, right? Phase difference, no phase difference, 0 or 360 degree. We have seen that it is 360 degree, no phase difference. And loop gain A beta is becoming equal to 1. So that's why you can expect a sustained oscillation from this circuit. And what will be the output of this circuit? Remember, the output of this circuit would be an sinusoidal wave. Okay. And what would be the frequency of this sinusoidal wave? That is already also we have derived. The frequency would be given by this expression, 1 by root 3 RC. Okay. So depending on the choice of value of R and C, you can vary this omega. Now what is omega? Omega is nothing angular frequency, and it is related to the linear frequency by this expression omega equal to 2 pi f. right? So then if you can find the omega, you should be also able to find what is F frequency, right? So this way you can design an oscillator for a particular frequency. I hope this part is clear to you. Okay. Now here is an important thing. That is, we have used 3 such networks, right? Why have we used 3 such networks? Is it not possible to use only 2 or more than 3? Okay. To answer that, let us focus only one of such networks. Okay. So, if we consider one such network like this, then here we can write, you see, this V1 by V in. By this we have already seen this. So, ultimately we can also write it like this. Then, if you try to find out from this part, what is the phase of this part? Okay. So, expression of this phase turns out to be tan inverse of 1 by omega RC. This is the phase of one of this block, right? Now here, what would be the range of this phi or phase? You see, when this R is extremely small, then what will happen? 1 divided by extremely small number. So you can consider this number would be very large, right? So tan inverse very large quantity, infinity is 90, right? The other extreme condition would be when this R is very high. When this R is very high, then it is 1 by very high number, so turns out to be 0. So tan inverse 0, it is 0. So ultimately you can see this phi can vary from 0 to 90 degree. But can it really reach 90 degree? No, because in that case R would be negligible. That is not practically possible, right? So always this phi would be less than 90 degree. Right? Phi is always less than 90 degree. Okay. So as a result, you remember the total phase shift we have to make 360 degree. In 360 degree, the inverting amplifier is producing 180 degree phase shift. So the remaining 180 degree phase shift has to be generated by this frequency selective network. Now one of such frequency selective network can produce less than 90 degree. So that ensures that at least we need 3 such units, right? Okay, now the question is it possible to choose 4? Why not? Choose 4, choose the values appropriately. Okay. Okay, now here please note one important information here, like why have we used these buffers? Okay, 2 additional buffers. We have used 2 additional buffers because buffers works quite extensively as an isolator. So this buffer can isolate this unit with this unit, right? So that means this second stage will not load the first stage. The third stage will not load the second stage or the first stage, right? It is basically isolating one network to the other network. You know that, right? This buffer has that property. So to isolate that, we have used these buffers. But is it really required that we always have to use these buffers in between? The answer is no. You can remove these buffers as well. And that is mostly being done in practical phase shift oscillator. So you can see here, you can see this diagram, the bottom diagram. Okay. Here, this is a practical phase shift oscillator, and here you can see we have removed these buffers. Okay. Then you can easily correlate this circuit with the previous circuit, right, by removing only the buffers. You can see here, this is the first RC network, this is the second RC network, this is the third RC network. So 3 RC network has been used here. So then phase wise, obviously you can say like this should produce 60 degree phase shift, 60 degree phase shift, 60 degree. This is 180 degree phase shift, that you can tell. But you probably, what you cannot tell is what would be now the value of this R2. Okay. What would be now the value of this R2. That you cannot tell now. Okay? That you cannot tell now. What will be the value? That you have to find. So to find that, what you have to do? You have to take this network, okay, with R connected like this, take this network and find its transfer function. Find the attenuation. If you find the attenuation, you will find something like this. See, this is the network. CR, CR, CR. If you find this attenuation turns out to be 1 by 29. Okay, so that means if this section is generating a attenuation of 29, then this section should produce an amplification of 29, at least 29, right, to satisfy the Barkhausen criteria. Then we have to choose R2 then this time, which is different. So here R2 by R, this now would be equal to 29. Earlier we have seen it was how much? It was 2. Sorry, it was 8, right? Here we have seen this is 8, right? The relation between R2 and R. But now this relation would change. That relation would become this R2 by R equal to 29. Okay. Earlier resonant frequency was 1 by root 3 RC. Now that would become root 6 RC. Okay. It is not difficult to calculate. You can follow the same process. Only thing is that here, while calculating the attenuation of the phase, what you have to do, you have to consider the loading effect of this on the first stage, this on the first stage, first and second stage as well. So how can you do it? Very simple. Follow this KCL, KVL only, right? Write the total equation, then express V3 in terms of V. Okay. In that expression, again you have to make a comment that this is the gain, right? And this A beta loop gain, then you have to find this A beta, right? This is basically beta. Then you have to find A, you have to find A beta, find the expression of A beta, then you will see it will also comes out to be an imaginary number. So what we have done earlier, you have to make sure that this part is not imaginary but a real number. So you have to make some part equal to 0, from which you will get the relation of this and this. So I hope this part is clear to all of you. If you have any question, please feel free to ask. Now, couple of important information. For example, this is the actually phase shift oscillator that you can see this. This is the phase shift oscillator. The same thing can be redrawn in this way. Just to give you a glance like impression, like this is that passive network beta, right? And to give you an impression that this is the active network, right, A. So I have drawn the same thing here, right? This is the active part and together with this is the passive part. Okay. Now couple of important information, we'll quickly go through it. This a phase shift oscillator can generate signal without any external input because it relies on the internal noise and positive feedback to initiate the sustained oscillation. For example, here we have not given any signal, input signal, right? For the first case, we have considered one input signal here, that is just to make our analysis easy. But later on we have seen that we have completely eliminated this V in. We do not need V in anymore. This is just for the at the beginning we have used it so that we can make these derivations. Then if there is no input signal, then the question is where from we are getting this output signal, a particular frequency sinusoidal signal, right? So that is because of this internal noise. And you know this noise means what? Noise means it's basically voltage fluctuations, right? Because of the thermal noise. And it's, if you see in terms of this frequency is quite broad, right? So there are some noise, okay, which has been getting amplified by this amplifier. Now that has been passed through an frequency selective network. This frequency selective network choose only one frequency out of it, then that is been fed back again to the amplifier, positive feedback. So that particular frequency signal again get amplified, right? So again that signal comes out to be, again only that signal can pass through it, frequency through the frequency selective network. Again that signal is getting amplified. So this is how, without, why we do not need any signal here as an input, but still without any signal we can produce and sustain oscillation from this oscillator. Okay. So I will go through it. A phase shift oscillator can generate signal without any external input because it relies on the internal noise and positive feedback to initiate and sustain oscillation. In any electronic system, there are always small random voltage fluctuations due to the thermal noise, even when no input voltage is applied. This noise includes broad spectrum of frequencies, meaning it contains components of many different frequencies, as I already mentioned. This tiny signal serves as the initial trigger. These oscillator consist of an amplifier, right? Typically an op-amp or maybe also an transistor and a feedback network, which made up of these three RC network. As I already discussed, less than 3 is not possible, right? This amplifier inverts the signal, so 180-degree phase shift, contributing 180-degree phase shift, while the RC networks provides the additional 180-degree phase shift. We discussed it all quite well, making the total phase shift around the loop 360-degree or 0. This satisfies the phase condition of this Barkhausen criteria. Additionally, the loop gain is adjusted such that it is equal to or greater than 1, slightly greater than 1. This satisfies the second Barkhausen criteria necessary for sustained oscillation, right? So I think then this paragraph summarizes quite well what we have discussed. Now, once this small initial signal is getting amplified and fed back through this RC network, it keeps circulating and growing until a stable sinusoidal waveform is established. The frequency of this oscillation is determined by the values of these resistors and capacitors in this feedback network. Given by this formula, we have already discussed 1 omega equal to 1 by root over of RC. So F would be equal to 1 by 2 pi root over of RC. As a result, the circuit maintains a continuous sinusoidal output signal without needing any external driving signal, right? So if this part is clear to you, then let us go to the next page and see another oscillator which does not use an inverting amplifier, which does not produce an 180-degree phase shift, but it produces 0 phase shift. So basically we will now use not an inverting amplifier but a non-inverting amplifier, right? Let's see that. So this oscillator is called an wine bridge oscillator. So the circuit of this wine bridge oscillator is shown here, right? You can see this here, non-inverting terminal, right, is grounded through a resistance R1, and we have also used this R2 connected with this output, right? And between this output and this positive terminal or the non-inverting terminal, we have connected an RC combination in series, right? And another RC which is in parallel, we have also used here, right? So this RC network part, which is in series, let us say the impedance is Z1 resulting in, okay, and here this RC network which is in parallel, let us say this impedance is Z2, okay. Then I hope you can understand. Then this is the part which provides the gain A, and this entire part is the part which provides this beta, right, the passive component part, right? Okay. Now as we are using here this op amp as a non-inverting amplifier. So this produce zero phase shift. Then to maintain the Barkhausen criteria, we have to also ensure then this passive network should also produce a 0 degree phase shift. Right? We'll see that. Now it is called as a wine bridge oscillator because it uses this bridge. Means you can also configure this circuit or redraw the circuit. Actually these two are the same circuits. Okay, same circuits, but it has been redrawn on to show that it actually forms and this bridge circuit, right? Okay. Now here to find out what is A, so basically A of S. So this is a non-inverting amplifier. So the gain is 1 plus R2 by R1. And what is the gain or attenuation provided by this passive frequency selective network? This beta is, as I mentioned, this is Z1, this is Z2. Then it would be Z2, right? The drop across this, right? It's basically the potential, like how potential would be divided, right? You consider the potential here is V0, how this potential would be divided between series combination of Z1 and Z2. See, basically Z1 and Z2 are in series. Simple potential distribution. So it will be Z2 divided by Z1 plus Z2, right? Now what is Z1? What is Z1? Z1 is this part R and C in series. So it is basically R plus 1 by j omega C means 1 by SC. So it gives out this. What is Z2? Z2 is this R and C parallel. So it is R into 1 by SC, R plus 1 by SC. So that gives this, right? Now if you have to find total loop gain, it is A of S and beta of S, right? A is this part, right? A is this and this part is this beta, right? Now try to simplify this, right? This part, try to simplify this part, right? And further simplification, this is another further simplification, right? Now here you can see this is what the loop gain, right? So this loop gain, again the process is almost the same. This loop gain has to be equal to 1, which is a real number, right? Then this expression should also produce the real number. Here see everything is real except this part because S is there, so j omega is there. So that way we can say like this would be produce a real quantity only when this part goes to 0. So that means this SRC plus 1 by SRC, that would give equal to 0, right? Then you just substitute the values of S, j omega RC, right? Then that would give you an expression of omega. So here what is omega? Omega turns out to be 1 by RC. So it is actually omega means omega during oscillation. So we have denoted this special omega is omega naught, oscillation frequency, omega naught, right? So omega naught is 1 by RC. Now at omega naught, what would be the magnitude of AS and B, means A beta, right, or the loop gain? Then what you have to do? You have to just put these things here from this expression, right? So it is basically R1 plus R2 by R1 into this part turns out to be 0. So it is becoming only 1/3. This is equal to 1. That turns out to be R2 by R1, that is equal to 2, right? So that gives the relation between this. This gives the relation between this R1 and R2. So we have seen this R2 would be equal to 2 times of R1. So that means it is providing a gain of 3, right? Yes. Is that part clear to you? If this part is providing a gain of 3, right, then this part also has to produce an attenuation of 1 by 3. Then only the criteria would be satisfied, right? If this is 3, then it would be 1 by 3. Total has to be, A beta has to be equal to 1, right? Okay. So we'll check that whether it is really 1 by 3 or not. The other thing is that as it is producing 0 phase shift, then you have to also ensure that this part also produce 0 phase shift. And that is indeed the case. Actually, if you calculate this V in and this V out for this RC and this parallel RC network, then as you can see from here, here we are plotting this V out and here for different frequency, right? So you can see this maximum V out is possible at the oscillation frequency, and at oscillation frequency the maximum output is 1/3 of V in. Then what is the gain? V out by V in is 1/3. So the attenuation, rather I should say attenuation of this circuit would be equal to 1/3, right? And what is the phase shift here? You see the phase that between V in and V out for this network at this resonant frequency or this omega naught is actually becoming equal to 0, right? So this at omega equal to omega naught does not produce any phase shift, and at the same time it produces the maximum amplitude, and the maximum amplitude is what? It is the 1/3 of the input, right? So that gives 1/3 is this. So what we can say, this beta is 1/3. What is this A, right? Gain, this A is equal to 3. So that makes A beta is equal to 1. What is the total phase shift? Total phase shift here it is 0. For the amplifier part, for this amplifier part, that is also phase shift providing by 0, right? So both magnitude loop gain criteria and the magnitude of this loop gain criteria, that it is 0 phase shift, both are satisfied. So that way Wien bridge can produce a sustained oscillation and you will get a sustained output waveform, okay, sinusoidal waveform. Now to just and very simple thing. So for example, if you need to design an 1 kilohertz this Wien bridge oscillator, then how do you choose different values of R, C, R1, R2, all this stuff, right? Now the thing is that you have to start, right? You are starting from the scratch. So you have to first choose the op amp, right? Choose the op amp, right? Then it is given this omega naught. Omega naught is what? Omega naught is 2 pi f naught. We know that. Omega naught equal to RC. Then this is equal to RC. So then f naught is basically this, right? And it is given that f naught is 1 kilohertz, right? Now to start with, we have to begin with something, right? So we choose that if we have suppose 0.1 microfarad cap that is available in our lab, so we start with that. So if that is available, then we have to also find what is the required R. Then we have to use this formula, right, to calculate the value of R. So R turns out to be 1.592 this kilo ohm, right? Then what about these values of this R2 and R1? This relation between R2 and R1 we already know, right? That the gain has to be slightly greater than equal to, slightly means greater than equal to 3, right? Then you have to choose R2 is 2 times of this R1. So if you are choosing this as say 1 kilo ohm, then this may be at 2.2 kilo ohm. Okay. So you can choose this different values of R, C, right? So such that basically you will get this 1 kilohertz sinusoidal wave, right? Now the thing is that if you want to change it, say want to make it 2 kilohertz, then what you have to do, just simply have to adjust this cap and this R. So same values of C and R you have to use it. Then it will generate a different frequency. But it has to be remembered that this Wien bridge oscillator is typically being used for gigahertz. Okay, not beyond that. So don't think that you can make something in gigahertz using these oscillators. Okay. That is not possible. Okay, so far what we have seen, that we have seen the oscillators which can produce a sinusoidal waveform. Now let us deviate a little bit from that and let us see that can we generate a square wave using an op-amp circuit? The answer is yes. So we can use this Smith trigger based oscillator to generate this type of waveforms. So to understand this, let us first just briefly discuss about this op-amp comparator. I hope that all of you are quite familiar with this op-amp comparator. So op-amp, it has two terminals, inverting terminal, non-inverting terminal, and suppose this non-inverting terminal is now connected with the input voltage, and with this inverting terminal we have used in voltage source, reference voltage source, V reference, okay, and this is the output. Then there is no feedback from this output to the input, no negative feedback, okay. Then what will happen? What will be the relation between V output and V reference and V input? This you know that op-amp is nothing but an amplifier, and the gain of this open loop op-amp is pretty high, right? Very high, in the range of 10 to the power 5. Then what is V output? V output is nothing but V in minus V output is nothing but this gain, which is very high, into V in minus V reference, right? So you can see then very small difference between these V in and V reference can produce a very large change in V output, right? For example, say this turns out to be say few millivolt, say tens of millivolt. So tens of millivolt and this gain is 10 to the power 5, right? Then what would be the V out? Then it from this it appears to be that 10 to the power 5 into 10 millivolt. So 10 to the power 5 into 10 millivolt, right? Millivolt means 10 to the power minus 3. So this would be this output voltage. So that turns out to be 10 to the power 3, right? Yes, right? So it turns out to be this output voltage will be pretty high, extremely high, right? But is it really possible? The answer is no, it is not possible. Why? Because the output voltage is limited by the supply voltages. You know, you also give the positive V supply, right? And you also give negative V supply. That would limit what would be the value of this maximum and minimum output voltage. So for example, if this is positive, then this output voltage would become a positive voltage. If this difference is negative, then this output voltage will also become a negative voltage. Now what would be that voltage? Can it really be equal to the supply voltage? The answer is no. There will be some drop. So typically this maximum output voltage would be slightly lower than this supply voltages. Okay, it cannot reach to the supply voltage. Okay, so we can consider that plus Vsat and minus Vsat. This is the maximum voltage that it can reach. Is that fine to you? Okay. Then what a comparator does is that if this V reference, see, if this V reference is lower than this V in, then this comparator would produce a voltage which is plus Vsat. Okay. Now if this V reference is higher than V in, means higher than the positive terminal voltage, then it would generate a volt potential at this output which is minus Vsat. Okay. That way it can compare this input voltage with respect to that of this V reference, right? Okay, so with this understanding, let us see this particular circuit. Let us see this particular circuit and try to understand the operation of this Smith trigger circuit. Yeah, one important point to note here, this particular circuit is not an oscillator circuit. It is simply an Schmidt-Trigger circuit. Now let us see this how this Schmidt-Trigger circuit operates. Now here one important thing is that see this output, from this output we have tapped, we have used two resistors connected in series, right? So basically then V out would be dropped across this R2 and R1, and between here we have taken another tap. From this we have taken this feedback and fed it back to the non-inverting terminal. So that means now it is in the positive feedback, right? Non-inverting terminal of this op amp. And here we are giving this input signal. Okay, right. Now, for example, let us consider that this V out, okay, this V out value is V high plus V set. So if this V out can take only two values, right, as I mentioned, plus V set or minus V set. Let us consider the output is plus V set. So if it is plus V set, then what would be the value of this V plus? I have denoted this as V plus because it has been connected with the non-inverting terminal of the op amp. So what is the voltage of this V plus? This is nothing but use the voltage division. So this V sat into R1 by R1 plus R2, right? So this would be the voltage at this node, right? And this voltage has been given as an input to the non-inverting terminal. Then this is basically, now if you consider this part, it is nothing but a comparator, right? Now it compares the voltage V in and this V plus. As I mentioned, if this V in is lower, if this V in is lower than V plus, right, then the output voltage would be same as that of this higher voltage. Higher voltage is being applied to the positive terminal, so this would remain as plus V sat. So you can see from here, here we have plotted this V in versus V out characteristics, right? So this is a 0 volt, V in 0, this is V in negative, this is V in positive. So suppose when you are going from V in negative, starting from V in negative, right? Then when this V is negative and compared, so this is a negative value, minus 1, and say this is at 2.5, okay? So minus 1 is lower than 2.5. Then what will happen? Then output would be high, this plus V sat. So it will sustain to plus V sat. Till what point it sustain to plus V sat? Till this does not cross this 2.5. Just for an example, 2.5, if this is 2.5, then until and unless it cross 2.5, it will sustain to this plus V sat. Now once it cross this 2.5 plus 2.5, just cross it, immediately you remember this negative terminal potential is now higher, so this output voltage immediately go from plus V sat to minus V sat immediately, all of a sudden, right? So you can see it here also, all of a sudden this potential will go back from this level to minus V sat level. Minus V sat level, this is plus V sat level, right? And after that, if you further increase this V in, then this will sustain, right? I hope this part is clear to you. Okay. Now suppose after this, now, okay, in this condition, okay, what is the output voltage here? In this condition, the output voltage here is minus V sat, right? So if it is minus V sat, what would be the V plus potential? The V plus potential has now no longer this, right? But it has now changed to this, right? Because this potential has changed, this potential has changed. So then this potential will also change, right? So now the reference point has changed. Earlier the reference point was this, now the reference point is this. Okay, now what will happen? If you reduce this V in, so if you reduce this V in, then what will happen? Till this V in crosses, this is, remember, this is 0 and this is some negative value. This crosses this point, right? It will sustain minus V sat value. Now once it crosses this, immediately after it goes back to plus V sat. Right? Now if you plot these two things together, it looks like this. Right? It comes like this, and while returning back, it goes like this. So you can see an hysteresis effect here. Right? So to understand it, or to basically to identify the points, we have denoted this term as VTH, V threshold high. We denoted this point as VTL, VTL, V threshold low, V threshold high and V threshold low, right? So you can see then depending on this input and output conditions, this threshold voltage are keep on changing, means the reference points are keep on changing. Now using this, we will try to develop our this Schmidt-Trigger oscillator. Okay? Okay. So then let's go to the next page. See that. So this Schmidt-Trigger oscillator, it is also known as unstable multivibrator because it don't have any single stable state. Means it will keep on rotating from the high to low, high, low, high, low. It is continuously toggle between high and low. So a Schmidt-Trigger circuit can function as an oscillator to produce an square wave output by incorporating this RC network in its negative feedback loop. Remember what is written here. RC network in a negative feedback loop. RC network is now used here in a negative feedback loop. Okay. This configuration lacks any stable state, means it will not produce say output voltage always high or output voltage always low. It will keep on toggling between high and low. So that's why it is called as unstable multivibrator. Now compared to previous circuit, the additional part is this, right? So here what you can see here, we have taken this feedback from this V out, right, through resistor and fed it to a capacitor which is Cx. And here we term this potential of this capacitor as Vx. Okay. And to simplify our analysis, we have considered that R2 and R1 are same and they are equal to R. Okay. And this plus Vsat we have now denoted as plus Vp, and minus Vsat we have denoted as minus Vp. I mean voltage peak, positive voltage peak and negative voltage peak, like that. Okay. Now let us see the operation of this circuit. Now if this V0 is low, see if this V0 is low, right, if this V0 is low, right, so that means what? This is working as in comparator, then V0 low means V0 would be equal to minus Vp only, right? So if this is minus Vp, then what would be the potential here? See, it is a voltage divisor circuit and these two resistances are same. So it would be just half of it. So it is Vp by 2, right? So this potential is no Vp by 2. Actually it would be minus Vp by 2, right? Because it is the potential, it is minus Vp, so it is minus Vp by 2. Right. So you can see here, then just consider, then this same Vx is feeding back till here. Now it is becoming as now it will working as an comparator, right, between this like, okay. Now here, as this V output is equal to minus Vp, so that means that minus Vp would try to induce across this Cx capacitor. So that means what? This, if say initially this voltage was 0, then this Vx potential would start decreasing. Right? See, that's what we have written here. Cx begins to charge, so that means Vx starts just a minute. Yes, it is right only, right? Yeah. So because of this, see, right, this Cx begins to charge and this Vx would start rising, right? This Vx would start rising, right? Okay. Then if we use the generic formula for an RC network, then using that Vx can be written as this V final plus this V initial minus V final into, it will exponentially charge. So exponential of this T by Rx Cx, because it is charging or discharging through this Rx and Cx. Right. Here this final voltage V final is the final voltage of the capacitor, the possible final voltage, not the practical final voltage. So what is the possible final voltage? The possible final voltage of this is that it would charge to plus Vp. What is this initial voltage? Initial voltage was that it would charge till plus Vp, right? What is this V initial? V initial was, what was the initial voltage of this cap? Initial voltage of the cap was what? It is Vp by 2, right? Minus Vp by 2. So it is minus Vp by 2. Right? What is V final? V final is, it is Vp, right? And then this part remain as it is. So if you just simplify it, it turns out to be this. Now this is the expression, one of the expression. We need the another expression after that. But before that, as this Vx is rising towards this Vp, as we have seen here, okay, this, when Vx becomes slightly greater than this Vp by 2, I hope you are getting what I am trying to say. I am trying to say that this Vx is rising, right? Now when this Vx is rising, right? When this Vx is rising, then what is going to happen here? Vx rising, right? When it towards Vp, because this potential Vp, when this Vx becomes slightly greater than this Vp by 2, then this output switch again back to the low state, right? Again switch back to the low state. Means now this Vp become equal to minus Vp, right? And this makes what? This makes this output voltage equal to minus Vp by 2. So that this Cx would start now discharging and this Vx would drop. So perhaps you can see this waveform, you will understand in a better way. See this. Right. This is the output waveform. This is how output waveform can vary. Output waveform can vary between plus Vp and minus Vp. Right. And what is the maximum voltage that it can reach? This Vx can reach. Vx can reach maximum voltage plus Vp by 2. What is the minimum voltage that Vx can reach? Minus Vp by 2. Why? This is the maximum and this is the minimum. That is because if this is Vp by 2 and when this potential is increasing, just immediately when it cross Vp by 2, then what will happen? This here, this output will toggle. Output would toggle from plus Vp to minus Vp, right? So as a reason, at the same time, what will happen? Because of this minus voltage, this Vx would start falling back. So you can see it here. So it is start rising. Now when it reach to this point, it is, if it is, that criteria is not there, then it should have charged till Vp. But we are using it as in comparator, right? So as soon as this Vp, as soon as this Vx is becoming equal to this Vp by 2, this comparator action kicks in. And that makes the output voltage equal to how much? That makes output voltage equal to minus Vp. When this output voltage becomes minus Vp, what is going to happen to the capacitor? The capacitor would again start losing the charge. Means the potential across the capacitor would start decreasing. The potential of the capacitor start falling down. Then it reaches to 0. Then finally, because of this negative potential, it would again charge in the other direction, right? Again here, right? When this output voltage is minus Vp, then what is the value of reference voltage here? The reference voltage here is minus Vp by 2, right? Now you see this voltage is falling, to from plus Vp by 2 to minus Vp by 2. Now when it reaches this minus Vp by 2, then see what happens. When it reaches minus Vp by 2, this transistor, this comparator action kicks in, and as this voltage has now become higher, right, it would make this output voltage transition from minus Vp to plus Vp, right? So when it turns minus Vp to plus Vp, so this plus Vp is connected through this Rx to this capacitor. So that would start building this charge across it. Means it will start rising the potential. So that means it can minimum reach till this Vp by 2. Then again it has to go back and charge till again plus Vp by 2. Now again when it reaches plus Vp by 2, again what will happen? Comparator action kicks in, again it will fall back. So as a result, you can see this charge, the potential across this capacitor, which is denoted as Vx, would increase, means charging, then discharging, then again charging, then again discharging, right? And as a result, what is going to happen to the output waveform? Output waveform would remain constant here till Vp plus Vp, then here minus Vp, then again here plus Vp, then again here minus Vp. Okay, and we have denoted couple of terms here. For example, we are saying at time t equal to t1, it is at the output is getting transition from high to low, and at time t2 the output is again getting transition from low to high. This would be required for the solution part. Okay, so then again we can use the similar formula for the other part, means for this second part, this stage. Earlier we have used it for this part, now we are going to use it for this part. Okay, so use it for this part. Now here, right, we have used this t1 is the time when this is transition from here. So just little bit simplification. Okay, you can see this. Then this Vx would given as this t minus t1 to t zeta. Now here this t is greater than t1. Remember that. Okay. Now if you can use this equation number 1, then equation number 1 says that this equation, right, and you know what is the value of Vx? Vx is nothing but this Vp by 2, maximum voltage, right? After that it has to again start discharging the capacitor. So just put here the Vx equal to plus Vp by 2 and put the time t, this time t equal to this t1, right? If you put that time equal to t1, then you will get t1 equal to Rxcx, resistance into that capacitance, into ln of 3. Okay, and ln of 3 basically is nearly equal to 1.1, so it is 1.1 Rxcx. Okay, similarly for this part, that is this part, okay, between time t1 and t2, okay, or even more specifically exactly at time t equal to t2, right, this potential Vx potential reaches minus Vp by 2, right? So put that criteria, okay, in this expression, then you will get t2 minus t1. So t2 minus t1 again it will comes out to be the same 1.1 Rxcx. So you can see this and this, they are same. So what does that mean? That means that here on time and off time they are same. That means 50% duty cycle. I hope you know what is duty cycle. Duty cycle is the of an oscillator is defined by the percentage of time that this output voltage in its high state. So the duty cycle becomes 50%. Then what is the total time period? Total time period means during which it was high and during which the time during which it was low. So it is basically T1 plus T2 minus T1, right? This basically both are same thing, right? 1.1 RxCx, right? So it is 2.2, 1.1 plus 1.1, 2.2 RxCx, right? Then what would be the oscillation frequency? Oscillation frequency is omega 2 pi f, right? What is f? F is equal to 1 by t, right? Now you know what is t, right? You can just write it. So it is basically 2 pi by 2.2 into RxCx, right? Now if you have to find then frequency, if you know that, you can find it. That is not a big deal. So I hope this part is also clear to you. If you have any question, okay. Then, so we have seen how to generate sinusoidal wave, how to generate square waves, and we have also seen how to change the frequency of these signals. What about amplitude? You can also do that by changing the simple resistors and capacitors value, not capacitor, on particular resistor. You can also change the magnitude. So magnitude and frequency we have seen how to change. Now the thing is that in different circuit applications, we have to modify the waveform, okay, or shape it differently compared to its original wave. We need that. So for that we need different types of this wave shaping circuits. For example, say this is an input sinusoidal wave that we have generated from one of our oscillators, right? And we have to use it in a circuit, but the circuit demands that the waveform cannot be like this, but the waveform should be something like this. Okay. So in that case, basically, I hope that you can identify what the change we have mentioning here, that it cannot reach till the full amplitude, here also the complete part, but it has to somehow get it clipped, right? Somewhere here, right? As you have rightly guessed. So this is what? This is a clipper circuit, right? So we need to use some clipper circuit to modify this waveform to this particular waveform. Okay. Now how can you do that? If you have to clip from this side and this side, then we know that we have to use some clipper circuit. Now what type of clipper circuit we have to use? How to connect? And the clipper circuit is basically what? Clipper circuit is nothing but circuit consists of diodes, diodes and batteries, right? Right. So then let us explain how this circuit is operating. So for example, if we choose this R here, okay, such that this R value should be able to limit the current that can flow through this diodes and these diodes. Okay, you cannot use any resistor here, right? Because each diode has a particular current carrying capability. So you need to limit the current, right? So you have to make sure that you are choosing this R value correctly. Another important point is that while choosing this R, that you have to ensure that this R value is not too large, because what will happen if this R is too large, then the current flowing through this R will produce significant amount of drop across this R only, then it would be very difficult to make okay, this circuit in operational. So you have to choose this value of R, be careful. Okay. Then we have chosen here two diodes in this fashion. One diode like this and another diode like this. Why we have used two diodes and in opposite polarity? That is because we can see that this is our output signal. We have to clip it in the positive direction as well as in the negative direction. So that is the reason why we have to use two diodes connected in opposite polarities, okay, in parallel paths. Okay, now with this diode we have also used batteries, right? Now why we have to use these batteries? Because we know the potential drop across this. If it is suppose only diode, then this maximum it can go till what point? It can go to this V gamma or the cut-in voltage for silicon diode, which is equal to zero point 0.7. But suppose this is more than 0.7, then we have to use an external battery through it. So we have to use a battery like this. Okay, so this is the reason why we have to use these components. Now regarding the circuit operation, let us see that. Okay, how this circuit is operating. Say now this Vi is positive. So for the positive half, obviously see this second diode is in reverse bias, right? So as the second diode is reverse bias, then what? As the second diode is reverse bias, so we should not bother about this during the positive half. We have to only consider the positive part for this part, right? This diode. Now this would try to make this diode positive, means the forward bias, right? But what about this battery, the other battery that we have connected? This battery has been connected, positive terminal has been connected with N. That makes this diode reverse bias, right? So one fight been going on between this Vi and this Vb, that who can dominate. Now, as long as this Vi is lower than this Vb, this diode cannot turn on, right? So this diode would turn off at that time. So then this diode is also off, this diode is also off. Then if this V in is increasing like this, then you can see the same thing is also being fed across here, that same path. So whatever is the increase in this V in, the same increase will also happen in the output, right? So the output would increase here in the same fashion, right? Okay. Now when this drop, okay, when this increase, suppose this is now Vb, okay. Now when this Vb, it will try up when it cross this Vb, Vi, when this Vi cross this Vb and tries to slightly move up, right? Then it also tries to make this diode in a forward bias, and this diode in a forward bias will produce another V gamma drop across it. So it will produce V gamma drop in a polarity, and here it is Vb, right? So that means when this Vi is actually crossing Vb plus V gamma, right? Then this diode, this part of the circuit is fully active. Then whatever voltage you will apply beyond this, right? It cannot change the potential drop across this part of the circuit, means it will be fixed to that point, right? So that's what we call it as clipped. It has been clipped to this part, right? Now, but at the same time this Vin is increasing, then when Vin will fall and fall below this level, that would again turn this diode off, right? As a result, this output would be same as that of this input part. So here also you can see this is the same as that of input part. This is how this part is working. Same thing will also happen in the negative half of the input signal. Here what will happen? We don't have to consider this part, but rather we have to consider this part, right? Here this, for this part again, this diode would be off, so whatever be the input, that would be followed at this output. After that, when it reach this VB plus V gamma, then it will be, then the diode will start conducting, and you know when the diode starts conducting, you cannot change the potential across that diode. So that would make the potential, keep the potential constant, right? But at the same time, this V in is further reducing, right? And when it will reduce, go beyond this, then again it will start follow this part. This is how the circuit works, and this is how it will get in operation like this, right? Okay, any question? Okay, now another interesting circuit is here. Please check this. Here you are providing a sinusoidal signal of Vm sine of omega t, right? Here this is the right waveform of the input signal. Okay, so it is this Vm. Okay, I think I forgot to write something here. So this is what? Vb 1 plus V gamma. This is what? This level. This is minus of Vb2 plus V gamma. Now it can happen that the Vb1 and Vb2 both are same. It can happen they are different. So if they are different, then this flipped part would be at different position in the right. It can be here, it can be here, right? Depending on the value of this. Okay. Now let us see this next one. It is also quite interesting, right? This is the input part, and can you guess what will be the output waveform of this? Now see, when this diode is first, we have to consider when this diode is turned on. This diode is here when it is positive, right? When it is positive, whether you have to on and off, and whether it is conducting or not, that you have to ensure that. Okay. Now, when this is positive, you have to also see this. There is another battery which has been connected here, and this battery, suppose if you nothing is there, okay, say gain equal to 0, then that battery will make this diode itself turn on, right? Because battery is for making this diode forward biased. So one current will flow. So till this part, this battery is making this diode conducting, right? Till that part, right? Till that part, you will not get any voltage across this. Obviously, we are not considering here gamma. If you are considering gamma, you will get an gamma potential across that, right? V gamma. We are not considering here. Then across this, there is no potential, right? So you will get the potential only when this input signal, this Vm sine of omega t crosses this Vb, right? Then only this diode would turn off, and whatever the signal is, you will get the signal there. I hope you are able to understand. So basically here this V output, once this diode is turned off, then this would be equal to Vm sine of omega t minus Vb. There will be, okay, this turned off. I hope, I am expecting that there is no drop across this. Then this would be the result of that waveform. Okay. So then what will be the result of that? It would be something like 1 minute, like this. This drawing is not perfect. I need to change this. Okay, so basically, let me also point these things out. When this is 0 volt, so beyond 0 volt only you will get this waveform like this. Okay, so this would be the V output waveform. And actually what this circuit does is that you can see this is Vm sine of omega t minus Vb, right? So this is Vm, right? So this is 0, right? And this is minus Vb. So from 0, you have to shift that waveform down by Vb minus, right? So basically then you can shift, and you know this diode only conducts, right? When this diode and you will get this one only when this diode is non-conducting. When this diode is not conducting, the diode is non-conducting only in this region. Okay. So that is the reason why you will expect a waveform, resultant waveform, something like this. I hope this part is clear to you. If you have any question, please feel free to ask. Then the next one, which is also quite interesting. So here, can you guess what would be the output waveform? Here it is given the input waveform is 6 sine of omega t in volt. Okay, so that means this is plus 6, this is minus 6 volt. Huh? Plus 6 volt, this is 0 volt. This is the input waveform. We need to find what will be the output waveform. Okay. So any case, how the output waveform would look like? See, so let's consider the positive half. Okay, the positive half. So when this is positive, this will try to make this diode forward bias. But there is another battery which tries to make it reverse bias, right? So that means till 2 volt, right? Till 2 volt, right? This battery would dominate and this would make this diode off. So when this diode off means no current is flowing through this, so that means whatever increase in this V in, that would be reflected back across this output. So that means at till plus 2 volt, you will get the output as it is. The output would follow exactly the input one. Now what will happen after, means once this V in is changing, right? V in is changing. When this V in has crossed 2 volt, now when V in has crossed 2 volt, you see current will flow through it, right? And when current will flow through it, it will also create a voltage drop across this, right? Then what will be the voltage drop across this? How can you find it? You know this voltage, right? Say Vm, okay? You know this voltage. This is V, not Vm is this maximum. Let us say Vi. You know this voltage which is V in, right? Then you know minus 2 volt has to be subtracted, right? Minus 2 volt has to be subtracted, right? And this current, and we are assuming gamma, V gamma, or the voltage drop across this diode is equal to 0. If not, then additional drop of minus 7, minus 0.7 we have to consider. Okay? Okay. So this is the voltage, right? And this is the voltage flowing through two resistors, 10K and 10K. But we have to only consider the drop across this 10K resistance. So the drop would be equal to 10K by 10K. So this is basically the current, this part by divided by current. This is the potential drop, right? Along with that, so this is the drop across where? This is the drop across this, right? But we have to find the drop across this. So this V naught is equal to what? 2 volt plus drop across this 10K, right? 2 volt plus drop across this 10K. So this is the drop across this 10K plus 2 volt. So this is, you see, nothing. This is but half, right? So basically V out here, V out would be equal to V in, half of V in minus 2 plus 2. So that means half of V in plus 1, right? Okay. What is the maximum voltage of this V in? V in maximum voltage is 6. So we can found what is this V out max. V out max would be equal to half of 6 plus 1. So that means 4 volt, right? So that means if we have to point some potential here plus 4 volt. So it can reach maximum till plus 4 volt, and then it has to again come back to this, right? And here again follow this one, right? Okay, what about in the negative half? Negative half, nothing, you see. In negative half, it is negative, right? This part is negative. So in this part is negative means the diode is already this off because of this, as well as now because of this. So you will get the entire negative half along this, right? Again here positive till plus 2 volt, you will get it. Then it will reach this plus 4 volt. Like that, like this waveform you will get. Now here please note one thing, this region, okay, in this region there will be a difference between this slope and this slope. Why so? Because it is no longer following the input potential, right? It is no longer putting this input following the input, but you can see this V out and V in, there is a half term, right? So the slope has changed. Okay. Okay. Then we are almost towards end of this. Another important circuit. So these are basically, I would say, let me write these things here, clipper circuits. Now here we will also discuss another wave shaping circuit, that is called this clamper circuit. Okay. So this clamper circuit is what? It basically uses capacitor, diodes, and as well as batteries. Okay. So batteries have not been used for the first circuit. So let us try to understand how the circuit operates and how it can and shape the and given input signal. Okay. So here this is the input signal which is given as this Vm sine of omega t. So peak amplitude is this Vm, right? Now there is a capacitor connected like this and a diode like this, right? Now what is going to happen? See, when this is started rising, right? Then this capacitor, which was initially say discharged, it will start building up the charge. So it will charge this side positive, this side negative with this polarity, right? Because now this diode is positive, forward bias, right? Because we are considering the forward bias. So, and also we are considering that here this V gamma is equal to 0. No potential, okay, across that. Okay. So then what is going to happen? This is diode, this voltage drop across VC starts building up. So it will build up gradually, and maximum voltage build up that is possible would be equal to the same as that of maximum input voltage, which is Vm. So if this is Vm, that same potential would gets built up across this capacitor. And for that, obviously it needs some time, right? Capacitor cannot charge all of a sudden, it needs some time. So let us consider that it takes, if it is t, right, this is the time period and this is the t by 4. Let us consider this t by 4 time period is required to get it completely charged. to Vm, this capacity. Now let us consider what happened after that. What's happened after that? Now when the input signal after that starts falling, right? But this capacitor will hold this charge, right? With a potential of plus Vm. Then what is the overall, like what can we write about this V output? Then we can write V output is nothing but this Vm, right? This Vm, okay, which has get charge, because you can see this is plus, this is minus. So right, so we have to take care of the polarity of this area. Plus this Vm sine of omega t, right? So whatever be the sine of omega t, we have to just substitute one Vm out of it. What is Vm? Peak potential, right? So when then this was charged till Vm, and here what is the magnitude of this signal? This one here at t by 4, this is also Vm, right? So this is Vm, this is Vm. Then what would be the output waveform magnitude? Output waveform magnitude would become equal to 0. So it becomes equal to 0. Then at t equal to t by 2, at t equal to t by 2, signal amplitude is 0. But signal amplitude is 0. But here, you see, then what will be the V output? This part is now 0. This is minus Vm. So this going to be minus Vm somewhere here, right? This is minus Vm. Okay. Then here at t equal to 3t by 2. At t equal to 3t by 2, here what is the amplitude? Here it is minus Vm. So it is minus Vm, minus of 2 Vm, right? So somewhere here minus 2 Vm. Then it will again follow, similar analysis can be done like this, right? Then the output waveform would look like this. So here one thing you note that it does not change the frequency of this circuit, it just shifts the DC level of this circuit, right? Earlier the DC level for this sinusoidal signal was 0, but now the DC level has only been shifted to minus of Vm. Right? So the DC level has been shifted. Okay? Okay. Then let us consider another important circuit. Okay. Here we have this Vm sine of omega t as the input signal. This is the capacitor. This is the diode. Along with diode, we have also used a battery. Now here in this case, what is going to happen? Analysis is going to be the same. Only thing is that we have to consider a couple of things. That when this diode can turn on for this case. For previous case, the diode can turn on as soon as this input signal become positive. But can the same thing we can also say for this? The answer is no, because here this voltage is making this diode in a reverse bias. So we have to cross this input voltage has to cross this VB, then only that this diode would turn on, right? And then this capacitor will start building the potential across it. Now say when this is turned on, say now this is turned on, okay, then what is the, if this maximum amplitude is Vm here, what will be the maximum amplitude or what will be the maximum potential that this C can hold? Now it is not anymore Vm, but it is Vm minus Vb. I hope you have understood this part. It is Vm minus Vb part, right? This can hold. Then the same thing, like previously, output voltage expression would become now what? It is Vm minus Vb plus V sine of omega t. So that means this input signal will now be level shifted by a potential which is Vm minus Vb. So that means if this is 0, then this level Vm minus Vb, this would be shifted. Okay, so the output waveform is this now, right? Now, if it is not say sinusoidal wave but and square wave, then what will happen? If it is not in sinusoidal wave but in square wave, then concept is same, right? There will be a simple shift in DC level, so it will also be shifted to a DC level. So the output waveform, instead of this 0, now it will start from this Vm minus Vb. Like this. Okay. So this will be the case. I don't know if I have time. Can I just take 5 more minutes? Okay. No answer, so I guess I can. So here, these RC differentiator circuits. Okay. So for example, if this is an input signal and this is an output signal, right? And this input signal has been fed to an RC network like this. Okay. Then this RC network would behave as a differentiator circuit. Okay. Now there, even though there is some assumption, I will discuss what is the assumptions are. The assumptions are that, like we are assuming the voltage drop across this resistor, that is VR, is much smaller than the voltage drop across capacitor. So that means Vc is much greater than this VR. So in that case, we can say this Vc is nothing but V in, right? Because this part is negligible, right? Vc is equal to V in. So if this Vc equal to V in, then what is I? Current through the capacitor. We know that we can write it C into dVc by dt. Right? Now what is this dVc? Vc can be approximated to V in, so it is basically C into dV in by dt. Right? Then what is V out? V out is nothing but IR, voltage drop. So just substitute the value of expression of this I, we can get RC dV in by dt. Right? So you see the relation between input and output. What is the relation? The output is proportional to the ddt of V. That's what a differentiator does, right? So then basically this circuit works as a differentiator. So here, suppose if you provide and square wave, okay, in the input side. If you provide and square wave in the input side, then what is going to happen? Then as soon as this potential, this turns on, right, means the signal become high, this capacitor starts building up potential charge, right? Then, but it takes some time, right? As soon as you just raise this potential, this capacitor cannot charge completely, right? It takes some time to build the charge across this capacitor. So that time again depends on the value of RC constant, right? Now say this, we have a reasonable RC time constant for this case. So if we have a reasonable RC time constant, or say high towards in the higher side, then immediately whatever be the voltage, that capacity, that and large amount of current will flow through the capacitor and it will create a voltage drop across this resistor. So here in that case, this VR would be now nearly equal to this V in. Try to understand, it will, because this capacitor potential, the potential across this capacitor is initially equal to 0, right? Then when this voltage is applied, this plus Vm, then this plus Vm has to be applied across this resistor only, and this is the same voltage as this output voltage. So you will get this output voltage, you will go immediately shoot up to this V out, right? Okay, it reaches V out, fine. Then what? Then, but this capacitor has been now connected within this source of Vm. The capacitor starts building up charge. Then what is going to happen to the voltage drop across this for this? Because the capacitor is building the potential across this. So the overall potential is constant. So this potential VR has to drop, right? And that you can see this VR potential is dropping across this here, right? This potential is dropping across here. Till what time it drops? Till it does not reach a very low value, or this toggles, means the input toggles. So when the input toggles, say for this case the input toggles, then what is going to happen? Now you have connected a source of this minus Vm with this. So the capacitor again, what it does, it will behave as a short circuit, because it is very high frequency, right, at this age, all sharp transitions, right? So you can see this current, it depends on this dV in by dt. So here this dV in by dt at these edges are very sharp. So the current would be pretty high. So current pretty high means that current would create a large voltage drop across this resistor. That means whatever be the input voltage, you can say the same input voltage would be drop across this resistor. So the same input voltage will drop across the resistor. You can see from here, right? So the you will get V out immediately like this. But after that, what happens? Now the capacitor again building up charge, right? Now in a reverse polarity. Earlier it was building this side plus, this side minus. Now it will be this side plus, this side minus. Opposite polarity. So as a result, what will happen? The voltage drop across this arc will also gradually start falling. So you can see the voltage drop across gradually starts falling, right? Again this toggles, input toggles again, right? Again the same thing happens here, right? It really does not look like a differentiator, means differentiated version of an square wave, right? Because ideally what do you expect? Only during the transition, because this during the transition here it is constant, right? So differentiation means here you should get ideally 0, but here you are not getting 0 somewhere. So here you should only get the values only during the transition, not when the values are constant. But it is not, definitely it is not an ideal differentiator circuit. But instead of using a high RC, if we significantly low that RC time constant, okay, then what will happen? Then what will happen? This discharge means capacitor would get charged very quickly, right? So capacitor charge very quickly means the potential drop across this R, the drop across this R, that will also reduce quite fast. So you can see it shoots up, just shoots up now, then decreases, then right. Again when polarity of the input reverse, go to the reverse direction, again it shoots up like this, right? Again it shoots up like this, right? So basically it would give you these spikes, right? So if you need this type of spike in some application, then this you can use this RC differentiator circuit. Okay, this RC differentiator circuit like this. Similarly, if you want to, instead of suppose and square wave if you use and triangular wave, like this, for this differentiator. Then you can expect you will be getting a square wave, right? Yes. So here the constant is that the RC time constant has to be much less than the time period of the signal. Now that's what we have seen, right? Yes. So hopefully you have understood this part. But as we have mentioned before, that here is an assumption. And the assumption is that this Vc is much larger than this Vr, right? And not all places this assumption holds true, right? So a better way to design a differentiator circuit would be to use an op-amp. Okay. So you can see the same actually configuration of R and C we have used, right? Same configuration of R and C we have used, but only addition to that is that we have used an op-amp as well. This op-amp has been connected in which mode? Inverting mode, right? Yes. So here this is V in, right? With the inverting terminal we are feeding the signal through a capacitor and this resistor, right? Then if you consider this op-amp as an ideal op-amp, so really not consume any current, right? No current can pass inside and go inside this op-amp. So basically whatever the current is flowing through this, right? The same current has to go out, right? Isn't it? Or in other way, we can say this current is I and this current is flowing from V0 to this, there should be the same current, right? Okay. So that basically, what is the current through this capacitor? So that is basically C into dV in by dt. What is the current, this current flowing through this? If we say this is high, then this V out, considering this V out high, V out, because of this virtual ground concept, this potential can be treated as a 0, right? So it is V0 minus 0 by R, V0 minus 0 by R. So that is equal to 0 because there is no other current. Right? That gives V out equal to minus RC dV in by dt. So it is obvious because you are connected in an inverting terminal. So you can expect an obvious minus sign. Right? So here you can see for this no such assumptions are involved, that you have to consider that entire voltage drop falls across Vc, not across Vr or not distributed, right? That assumption is not there. The last one is this RC integrator circuit. So just replace the position of R and C in the previous interchange, right? Interchange the position of R and C in the circuit, in the previous circuit, that would give you an integrator circuit. Now why this circuit behaves as an integrator circuit and what is the assumption? Here the assumption is that for this analysis, assumption is that this Vc is much lower than Vr. So that means the voltage drop across this cap is much low than this voltage drop across this resistor. Why so? That you will understand just now. So what is V in? V in is basically the voltage drop Vr plus Vc. Now if we have assumed this part, then we can write this V in is nothing but equal to Vr. Now what is I? I is, if this is Vr by R, so what is Vr? Vr is equal to this Vi, this is equal to R. Then what is V out? V out, if we know the current, this same current has to flow through the cap, right? Same iron current. So if we know the current through the cap, then we can find the voltage develop across this capacitor. So that is equal to V0 equal to Vc, and this is equal to 1 by C integration of I dt. Then just replace this value of I what got here. Right? Now please try to understand why we are saying that we need these assumptions. We need these assumptions because this here we can write this V output is proportional to Vi only because of these assumptions. Okay, if Vc is also quite significant, okay, then we cannot make this, write this, right? V in is equal to Vr. then you cannot write this I is equal to Vi. Then it should be this I is equal to Vi minus Vc, right? So then you will not get this expression, right? So that's why here is the assumption, when this is the assumption for this circuit to operate as an integrator. So then what do you expect as an integrator, right? So if you give a square wave, then you expect the output to be a triangular one, right? But see, if this time period of the signal is quite high, okay, compared to the RC time constant, then here what is actually happening when you turn the signal to the positive direction, right, to the positive direction, this capacitor start building up the charge, and this potential drop across this cap is nothing but the output voltage, right? But the charge across capacitor you can't build all of a sudden. It takes some time to charge the capacitor. So it takes some time to build the potential across this cap. It cannot build all of an instantly, right? It will exponentially build, right? 1 minus exponential t by RC. So you can see this is building exponentially and reaching towards this value, right? The maximum value. And then when this input toggles to the negative half, then it again discharges and goes back to this level. Then it again charges and discharges. But this output wave from whatever we have uh, like obtained from this circuit is really very far from that of triangular circuit, right? So then what is the solution? The solution is that if we cut short this part of the time period, means if we make this time period really small, right, then it looks like this part really an straight line, right? If we can again reduce this part, then again it looks like this part as a straight line, which is quite close to that of a triangular wave. So you can see here, if we really reduce this is t by 2. If you really reduce this t by 2 or this time overall time period, right, then what happens? The signal waveforms become, output waveform become like this. This is quite close to that of a triangular wave. But here one thing is important is that if we do that, you will also sacrifice on the magnitude of this output voltage, right? Because you can see from here, you really are not going till this maximum VEM, right? You have to toggle it before, means the input is toggling before the output reaches to the peak input, right? So here the condition is that RC has to be much higher than this T, time period of the signal. Now again, like previous case, we can also design this op-amp using an integrator. Means we can use a op-amp to design an integrator, right? And this is the circuit using an op-amp as an integrator. Similar to the previous one, differentiator, only thing is that interchanging the position of R and C. So this is V in, this is V out, this is R, this is the cap, this is the current, that is I flowing through this. This is I, the current which is flowing through this cap. And you know, no current, ideal op-amp, no current flowing inside, right? So basically this current is has to be the same current, right? Then again, this is ground, right? Virtual ground concept. This is ground. So this point is also virtually grounded, right? Then what is the current flowing through this R? It is basically V in minus 0 by R. So V in plus the same current. What is this current flowing through this? We know the voltage here is V naught. So it is V naught minus 0. So C into dV naught minus 0 by dt, right? That is equal to this. Then from here you will get V output expression is equal to minus of 1 by RC integration of this VI dt. Okay. So you can see here this output is related to this input, integral of this input, right? But here no such in this circuit, no such assumption is involved like this. Right? So then with this we are at the end of our discussion. So in today's discussion what we have seen? We have seen how, means what are the components of signal generators, different components of signal generators, what is the basic principle of oscillations, both for positive feedback network and negative feedback network. We have seen the criteria for oscillation, but which is the nothing but the Barkhausen criteria, right? Then we have also discussed in terms of circuit level how to implement it, right? How to check whether there is a possibility of getting any oscillation or not. Then we have also discussed the phase shift oscillator, right? Using buffers to remove the loading effect, right? We have derived these expressions. We have also seen like what will be the minimum number of these RC stages for this phase shift operator, for this phase shift oscillator, right? Then we have also briefly discussed the phase shift oscillator after removing this buffer, right? Then we have also discussed like why we don't need any input signal, why without having any signal also we are getting the sustained output, and why the output is sinusoidal. Okay, because this is the most fundamental frequency. The sinusoidal is the most fundamental frequency, right? After that, it is that keep on using the frequency selective network, which is boosting only one frequency of the sinusoidal signal, right? The fundamental one. We have also discussed this Wine bridge oscillator, right? How this oscillator works, and these different criteria for its oscillation, different magnitudes, attenuation, phase, then how to design a specific wine bridge, simple wine bridge oscillator. Also briefly discussed about comparator, Smith trigger, and using Smith trigger, how to design Smith trigger oscillator, right? Which is also known as stable multivibrator. We have done the detailed derivation, right? And also we have discussed in terms of waveform how to design. In wave shaping circuits, we have discussed different clipper circuit, right? Different clamper circuits, differentiator circuits, and integrators, right? So with this, I think we are at the end of today's discussion. Please let me know if you have any question, doubts. Okay, then if you do not have any doubt, then let us end it here today. Thank you very much for your time and for your attention.